we present our work, Robust Feature Tracking in DVS Event Stream using Bezier mapping. The dynamic vision sensor is an imaging sensor that responds to local changes in brightness. It does not capture images using a shutter as conventional camera. Instead, each pixel inside an event camera operates asynchronously, reporting the brightness changes as they occur. It has microseconds temporal resolution, high dynamic range, and do not suffer overexposure or motion blur. In this work, we addresses the novel feature tracking method using only the event stream. This is the contributions of our work. First, we propose the event patch alignment algorithm for short-term tracking using the Bezier curve and the variance maximization. Second, the accurate temporal update method is proposed for the long-term tracking. Finally, we evaluate the proposed method both in the synthetic and real dataset. Due to the low latency of event camera, the events occurs almost continuously in time axis. Therefore, we choose to parameterize the trajectory of event patch in XYT dimension with a Bezier curve. By doing this, we can estimate the more time continuous trajectory. To this end, in the short-term tracking, we align the event stream in the direction of maximizing the variance of patch, simultaneously associating the events and estimating the trajectory of features. We process the long-term tracking using the temporally updated template patch. In this step, we first align the current events to the template with variance maximization, similar to the previous step. After that, we update the template again and use it for the next time. By doing this, we accurately update the template patch and boost the long-term tracking accuracy. We make the template patch by summing up the fixed number of recent templates with different weights. Each weights are measured by the exponentially decaying function. In the experiment, we first conduct a simple test of event alignment, comparing ours to two different methods: align the events with the line and simple stacking without any alignment. As you can see, our method aligns the events better than that of others, both quantitatively and qualitatively. We can see that the texture of the patch is best structured in our method, and also the mean variance of ours is the highest. For the template update experiment, the well-structured patches are constructed by using our method, while it is not consistent without using it. This is the quantitative results in the synthetic dataset. The datasets are collected by using the event camera simulator proposed by the Rebek and his colleagues. Using this, we quantitatively evaluate our method. As you can see, the result of our method outperforms the JUICE method in both error and tracking age with large margin. This is the quantitative result table in the real datasets, and our method shows similar or slightly better performance. This is the example of the qualitative results, and the graph shows that the comparison of ours and JUICE method. We apply both methods to the camera pose estimation problem using P3P and motion-only bundle adjustment. The estimated poses using our method shows better performance in terms of the accuracy and the number of inliers. Thank you for hearing my presentation.